Okay, so right now you're graphing the a plus b i's. I'm just repeating myself because I forgot to hit record. So you guys are just trying a few of them. Z equals a plus b I. We think of that a, b as x, y, and we're just plotting these points to the right 3, up 4. Left 4, up or down 0. Left or right 0, up 2. Okay, so real axis, imaginary axis, and putting real and imaginary together is called complex number, and that's called z. So z equals a plus bi. Okay? Yes? No idea. Yeah, I don't think it's anything on purpose. Probably just she made a typo there. I don't know. Is this exact problem that how would I know? I don't know. Mm-hmm. Well, that wasn't the AP exam test. That was a mock exam. It is. Yeah. We don't know what questions we're going to get. We have to cover lots and lots of things. But, for example, this question right here that we just did, that was really, really easy, we don't have one exactly like it in our homework. This is one part of a bigger question. So it might have been on there, but you just didn't recognize it because you hadn't learned it yet. But it might not. I mean, there may not be, they give us like percentages of certain types of problems that will be on there, or percentages of how much of the AP exam will come from unit 1, 2, or 3. But within there, we have no idea what they're going to cover. Just like any test. Like I cover a ton of material in the class. I might not give you every single question on the test. That's just impossible. Okay, so what I want you guys to see is this. This is the moment I want you to make a connection between all the different letters we call the same parts of a right triangle in this class. I mean, tons of them, okay? And they're really interchangeable. So, for example, let's just draw a right triangle here in quadrant 1. Theta is at the origin. And, a right triangle, go back to geometry when you were introduced to them. A squared plus b squared equals c squared. So you called this a, b, and c. In trig, we called it cosine squared x. We called this y squared, or sine squared x. We called this 1 because it was unit circle. Last week, we called it x, y, and r. So we get x squared plus y squared equals r squared. Bottom line is, we've called this x and y for a million years. Well, guess what? X and A are interchangeable, Y and B are interchangeable. So anything that has to do with X's and Y's has to do with A's and B's. You're going to see that over and over again. And oh my gosh, what all the different things we call this. Like I just went through them all, but most recently we called it R. We're going to call it R again in a minute, like radius on a polar graph. Remember how many circles you go out? But in complex numbers, we call it the absolute value of z, and I'll explain where that comes from. So just to back up, we were introduced to complex numbers today called z, and then we had the real and the imaginary part. And to get to that point, we went to the right a, up b, and that got us to the point z. Well, what if I want to find the hypotenuse of this right triangle? Well, we would use Pythagorean theorem, right? So that would be a squared plus b squared equals z squared. So this new formula that you're about to see is just a modified version of that. It's actually the easier way of doing Pythagorean theorem. It just takes us to the step where you just plug the numbers in. You don't have to actually like subtract anything or whatever, take the square root. Because think about what the next step of this would be. We would do the absolute value. Absolute value simply means the positive answer. A hypotenuse, a radius, they're always positive. It's a distance, okay? So absolute value just means we're going to keep the positive answer when we take the square root of that side. So this new formula is just Pythagorean theorem. That's all it is, okay? So that's one of two formulas we're going to be using today. And the other one is right here. Remember what I said, A's and B's and X's and Y's are interchangeable. How many different ways have we seen tan? We've done tan of theta last week was y over x. I'm not going to write it, but we also had tan of theta equals sine over cosine. We've seen tan so many different ways. It's still the same three sides of a right triangle. Depending on what category of right triangle, polar, rectangular, complex. It just changes the letters, okay? So let's take that a step further. Turn the page to example 11. We have to find the absolute value of z and theta, and then we're going to graph, okay? So let's start by graphing. I think that's the easiest, and it helps with these two, and you'll see why. This is page 158, sorry, for those of you that are looking for it, page 158. So I know it's a pain with these papers, guys, so figure out how you want to organize. Just know, if we're on an even page, and I'll try to keep saying what page we're on, you're going to have to find it on a green piece of paper. Your even numbers are on the green paper if you've got one of the unlucky packets, okay? Yep. This is 157? Oh, okay. This is 157, so thank you very much, Natalie. 157. Nobody corrected me till this period. Okay. So it's weird. My pages don't have your page number, so I always have to get it from students. Okay, whatever. No, correct me. This is kind of like first period. This is kind of like first period for me. Yeah. It would be way back. It would be on the other side, I think, of one. Is it on the other side of 155 for you guys that have? So 155, and then it should be 157 on the other page. You got it? Okay. I think I figured out all the issues, so I'm pretty sure you should have that. Okay, good. All right, so let's graph this first. Remember the a plus bi? There is no a. There's just a b, right? I know that's b because of the I with it. So that point would be down here at wherever negative 7 is. Okay, so just a rough little, there it is. That's the graph of that point. All right, now let's find the absolute value of z. Remember, the absolute value of c is just a squared plus b squared, then find the square root of it, okay? So the absolute value of z would be a squared plus b squared, which is the square root of 49, which is 7. Okay, we found that. That should make sense. Going down 7. All right, let's do tan. Tan of theta, sine over cosine, y over x. What are we dealing with? Okay, now we've got b over a. All the same stuff, just different letters. Now, when we get a 0 in our denominator, that means tan is let's just abbreviate, undefined. So the question is, where on the unit circle is theta undefined? Now, the truth is, theta is undefined up here at pi over 2 and down here at 3 pi over 2. Let me remind you of why. And that's not something I memorize like the other tan tricks. I just know if I get a 0 or an undefined, it's going to be a quadrantal. And what I would do is kind of think about my ordered pairs and know, oh, okay, at the top and at the bottom, when I do y over x, b over a, whatever you want to call it, I get a 0 in my denominator. So here and here, my tan value is undefined in the rectangular world. Well, it's going to be the same, it's in the same place in polar world. Remember, our rectangular points and our polar points are in the same exact place. So what would theta be for this question? Three pi over 2. What is the theta that has an undefined value for tan? That's down here at 3 pi over 2. How did I know it was this one and not that one? Because that's where my point is. Remember, the point on the rectangular and on the polar are in the same exact place. So that is our theta. So we found the radius, also known as the absolute value of z, also known as the hypotenuse, blah, blah, blah. And we found theta for that point. What would the angle be? It would be 3 pi over 2. Okay? Remember I said if I cut them both out and put them on top of each other, they'd be in the same place. Right? All right. So what we did last week is we went from polar to rectangular, rectangular to polar, not with imaginary numbers, just without those. So polar to rectangular and vice versa for ordered pairs and for equations. We're going to do the same thing with the complex numbers. Super, super straightforward, especially if you were here last week and understood it. So let me draw another triangle in quadrant 1 so we can use it to look at. Okay. Again, we've been calling this X or Y. For the purpose of what we're talking about now, I'm going to call it A, B. And I'm going to be switching from rectangular to polar. So instead of calling this the absolute value of Z, I'm going to call it R. It means the same thing, but I want to respect what form I'm in and what letters. Okay, and here's why. And you'll never have to repeat this, show this. I want you to kind of understand the connection though. So if you remember, in SOHCAHTOA, cosine is adjacent over hypotenuse. So adjacent would be A, and our hypotenuse we are calling R. And I'm going to multiply both sides by R. And what I have left is A equals, R cosine theta. That should feel kind of familiar. We had the same conversation last week, except it was X equals R cosine theta. X and cosine go together. Well, X and A are the same thing, right? A and X are the same exact thing. All right, same thing with sine. Sine is opposite over hypotenuse. So that would be in this picture, we called the opposite side B. The hypotenuse we called R. And we get B equals R sine theta. Same idea, B and Y are the same thing. So last week this said X and this said Y, but it means the same thing, okay? So what we're going to do, so this was rectangular form, right? A's and B's. So let me repeat that. I don't know if I already said it. We learned, something I was trying to drill into your head the last few days of last week was rectangular has X's and Y's and polar has R's and thetas, right? X's and Y's, R's and thetas. Well now, same idea, but instead of X's and Y's, we have A's and B's. And then we still always have R's and thetas for polar form. So going forward, if you see an A, a B, or X, or a Y, that's rectangular, okay? R's and thetas, polar. So here again is rectangular form of a complex number. Complex means it has the I in it. Let's substitute in for A and B, and that will give us polar form, okay? So Z equals, in place of A, I'm going to put R cosine theta, plus B is R sine theta. We typically put the I first. I'll talk more about that in a sec. If you already wrote it at the end, it's not wrong. So that's one way of seeing it written. Kind of a shortcut way of writing it is factoring the R out, since it's the same for both of them, and writing it like that. So these are both polar form of a complex number. Again, complex just means there's an I thrown in there. Okay? Okay, now let's go between the two forms. So our last page. Let's go between the two forms. I'm writing. And we'll apply this. So again, you don't have to show me like how these two are related, but now you've got some formulas that pretty much match the ones we learned last week. All right, first one, example 12. Here is a complex number. We got it. There's an I in it in polar form. We know that this is rectangular form because there's no thetas or r's. It just looks really different too. So if this is rectangular form, oh, what page is this? Oh, maybe I messed up on that. Maybe this was what I was looking at when I saw that. So this is 158. Now scoot all around, y'all. Find that page. Sorry. So if this is rectangular form, we have A and we have B. Remember, this is A plus BI, so 1 would be the number in front of our I. What we need is R and theta, and we're going to use those formulas that we just were talking about. Well, R is just the hypotenuse, right? This is a right triangle here where we go to the right the square root of 3, up 1 to get to this point. And we are in complex numbers, so we called this the absolute value of z. It is, but it's also r, okay? So r is better to use because we're going from rectangular to polar. And in polar, we always call that r, okay? But it is the hypotenuse and all the other names we've called it, okay? A little thing I always say is, like, to help you guys, like, it doesn't matter if you call that radius, if you call it c, if you call it hypotenuse. There's so many different names for that side of a right triangle, as long as you know what letters to use with the right forms. For example, my name is Tracy, right? People call me Tracy, I answer to that. My sister and my best friend call me Trey. The only two people. For some reason, they shorten my name to Trey. Other family members, other friends, all call me Trace for short. All three names mean the same person. I answer to all three of them. So it's just different nicknames, I guess you could think of for that side of the triangle, depending on the situation, okay? So let's use our little modified Pythagorean theorem. It's so much easier, right? It's already squaring the other side, and that's a squared plus b squared. That would be 4. So my radius is 2. Oh, sorry, I have to square that. Right. So the square root of 3 squared is 3, 1 squared is 1, 3 plus 1 is 4, square root of 4 is 2. Right? Then we use our tan formula. We did these same exact problems last week, we just called the letters different things. So instead of y over x, we're using b over a. They mean the same thing. William. I don't recognize this. I mean, I do, but if you didn't recognize what this is, you would need to rationalize the denominator, and you would get this. We see this a lot. 1 over the square root of 3, if you simplify it, gets to this. You might remember it from last week. So the question is, where on the unit circle do we have a tan value of the square root of 3 over 3? That's my denominators of what? 6. Okay, now I just need the numerator, because there's 4 denominators of 6. There's 2 that are positive, okay? But remember, this point, the original point, is in the same place as this angle. So since this is quadrant 1, this is quadrant 1. So this is pi over 6. Now we have what we need to write in polar form. Polar form, we need r and theta. So z equals r cosine of pi over 6 plus I sine of pi over 6. And that's it. That is the final answer. Now, the thetas here are always the same, always. And we typically see I in front of sine in polar form, but if you wrote it behind the pi over 6, it's not wrong. Okay, as long as the second term, the sine term, has an I somewhere in it, that's what matters. Okay? All right, let's do another one of those. A is the square root of 6. B is negative square root of 2. If I graph that, that's to the right is positive down. So I'm going to be in quadrant 4, which this is telling us that anyway. To the right, the square root of 6, whatever that is, down square root of 2. And now I need the radius, or the hypotenuse, or whatever. R equals square root of 6 squared. What do you say? Get back where?
Get back to your
I don't think calling it a cage is going to sell it too well. Get back into your cage, animals. Okay, when you square the square root of 6, you get 6. When you square the square root of 2, you get 2, which gives you 8. Remember, 8 is the square root of 4 times 2, which is 2 square roots of 2. Last week we talked about, you're going to see that all the time. You need to get comfortable with the square root of 8. It's a really popular radical, and it always simplifies to 2 square roots of 2. So you don't have to show the work, you just know that. All right, some fancy algebra, not really, basic algebra, but a good amount of it. Tan of theta equals y over x, sine over cosine. What am I using? Oh, okay, now I'll just use b over a. I don't recognize this. Whoops, that's a square root. I don't recognize this. Let me clean it up, just like I did on the last one. So I'm going to multiply by the square root of 6, rationalizing the denominator. I can multiply the 2 and the 6 together. That gives me 12. Square root of 6 times the square root of 6 is just 6. I'm going to simplify the square root of 12, because it can be, because I still don't recognize this. There must be something else I can do. That's 4 times 3. The 4 comes out, becomes a 2. Still don't recognize it, but there's one more thing I can do. 2 over 6 is 1 over 3. That I recognize. That is a denominator of 6, and we are in quadrant 4. To the right and down is quadrant 4, so I want the theta in quadrant 4. So that's 11 pi over 6. Now I have everything I need to write my answer in polar form. Let's do our r times cosine of theta plus I sine of theta. Okay, those are the harder ones. I mean, not that that's hard, but there's more work involved. We're just going to do one more as our last one, going from polar to rectangular. Okay, these are the quicker, easier transitions. So in this example, even if they didn't tell me what it's in, I know it's complex because it's got an I in it. So complex means there's an I in it. And I see thetas, so I know that this is polar. Okay, so I need to get rid of the r and the thetas. It's really simple. All I have to do is substitute in what cosine and sine are of 3 pi over 4. So 3 pi over 4, you don't have to write this, I'm just telling you where I'm getting these numbers. Right off the unit circle would be that on quadrant 2, so cosine, sine. So I would have 5 times cosine of 3 pi over 2 is this, plus I times sine of 3 pi over 4 is that. And let's just distribute. So I would have negative 5 square roots of 2 over 2 plus, you can keep the I in the front, you can put the I in the back, as long as there's an I, that's what matters. 5 square roots of 2 over 2. If you're going to put it in the back, be careful that it's not under the radical. Okay, it's 5 square roots of 2 times I. So it stands next to it, but don't put the roof over the I. Okay? And that would be your answer. We went from R's and thetas to A and B. A and B. Okay? All right. Homework is on page, let's see if I got this one right, 164, which is on the piece of paper I gave you last week. I'll be good for the last 2 classes of the day. Okay, so I'll do number 1 with you. So this is kind of what I was saying, Dylan. Sometimes the questions just like incorporate a whole bunch of things at once. Like, for example, this is graph it and write it in polar form, okay? So let's start by graphing it. This is A and B, right? To the right 2 up the square root of 3. Since I have like a nice graph here, I'm going to just put in my calculator the square root of 3. When I do the square root of 3, I get, 1.7. Yeah. So square root of 3 is 1.7. So I'm going to go to the right 2, up 1.7. There's the point. Graphing a point, nice and simple. Okay. Now, if I want to write this in polar form, I need r and I need theta. That's what I need. So using a and b, I know how to find r first. That's a squared plus b squared, which is 4 plus 3, or 7. So r is the square root of 7. Then we use tan of theta equals y over x. Nope, we're using b over a to find our theta. Now, I don't recognize this. I don't have a tan of square root of 3 over 2. I have sines and cosines of square root of 3 over 2, but I don't have tans. And there's nothing I can do to simplify it. It's not like I can clean up the problem like we did in those two examples. There's nothing I can do to this that's going to make it look like something on a unit circle. When that happens, you find it on your calculator. You're going to get a decimal approximation here. So whenever you're trying to find an angle, don't forget you use your second button. This is inverse tan or arc tan. So I'm going to use my second tan. Always want to use that if you're looking for an angle. Square root of 3. Now, if you hit divided by 2, at least on this calculator, I don't know about the newer ones, it keeps it under the radical. The 2 is not under a radical, so I'm going to arrow over, then hit divide by. So just make sure you know what your calculator is. And that gets us 0.714. There is the theta. So now I have everything I need to put this in polar form. So that would be z equals my r times cosine of 0.714 plus I sine of, I got it, 0.714. Alright. So this shouldn't be too bad. And a lot of time to work. I'm going to come around with the red folders, so if you need one, let me know. I'll give it to you. And make sure you have 5 colors in your folder, and you put your name on and period on the tab, please. Folder.